In this video, we are going to find non-negative integers a, b, c, and d, such that 4 to the power a plus 5 to the power b plus 6 to the power c equals 7 to the power d. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. First, I'm going to take mod 3 on both sides. So we can take a look at each term in this equation. For these two terms, 4 to the power a and 7 to the power d, because the base is congruent to 1 mod 3, no matter what the value of a and d are, they are both congruent to 1 mod 3. Same for this. For 5 to the power b, it can take two possible values, which are 1 or minus 1, because 5 itself, the base, is congruent to minus 1 mod 3, and if the index, the exponent, is an even number, is an even integer, then the whole power will be congruent to 1 mod 3 instead. Whereas for this term, 6 to the power c, if the index is 0, then 6 to the power 0 is 1, so it's congruent to 1 mod 3. But otherwise, since 6 is a multiple of 3, then its power, if the power is positive, then the value will be congruent to 0 mod 3. Now notice that if, for this equation, we take this number 0, then it will be impossible for the equation to hold, because no matter we take 1 or minus 1, and we add 1 and 0 on the left, we can't get 1 on the right. I mean, we can't get 1 as the sum, and so it won't be equal to that on the right. That means we must take this one, so that when we take 1 and minus 1 for the other two terms, then the sum will be congruent to 1 mod 3. Then that means, on one hand, we've got b to be odd, at the same time, we have c equals 0. So now, our equation becomes 4 to the power a plus 5 to the power b plus 1 equals 7 to the power d. And in particular, b has to be an odd integer. Next, for these terms, I'm going to try to take a look at the parity. For these terms, 5 to the power b and 1, and 7 to the power d, they are all odd numbers, always, no matter what the exponents are. And so that means I must have 4 to the power a to be odd as well. But that's impossible unless a equals 0, or else for positive exponents, then 4 to the power of that must be an even number. So that means, again, a equals 1, sorry, a equals 0, so the power equals 1. So therefore, 5 to the power b plus 2 equals 7 to the power d. And rearranging, we want to solve this. To solve this, of course, we can quickly observe that 1, 1 is a solution, and perhaps it might be the only solution. Then, to check whether, to justify that there can't be any other solution, maybe we can try to justify that we can take a look at what happens when b is at least 2. So when b is at least 2, then one thing that we can tell about that power is that 5 to the power b must be a multiple of 25. So that means 7 to the power d must be congruent to 2 mod 25. Now, notice that in general, power of 7 must be either congruent to starting with 7, the next one will be minus 1, because 49 is minus 1 more 25, then it's minus 7, and finally 1. It can't take many possible values, and all of them cannot be 2. So that means this assumption is wrong. That means b must be 1 or 0, but of course b is odd, as we have proven earlier. So that means b equals 1, and consequently d equals 1 as well. Then we can quickly check 4 to the power 0 plus 5 to the power 1 plus 6 to the power 0 is indeed equal to 7 to the power 1. So the solution set 0, 1, 0, 1 is a valid solution, and this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.